Alrighty, chapter 8. Let's see, confidence intervals. So 8 was not too bad. Most of it's calculator stuff. Let's see, 8.1. A single population mean using the normal distribution. So in this module, we learn how to calculate the confidence interval for a single population mean, where the population standard deviation is known. When estimating the population mean, the margin of error is called the error bound. Okay, so we've heard of margin of error. That kind of gives us a window of, we're just really estimating what values, what range they could lie in. We're not sure, but if we have a big margin of error, then we give ourselves a big window. Small margin of error is better, it's more accurate. You've got kind of a tighter range. So the margin of error depends on the size of the sample. So the larger the sample size, the tighter your window, the more accurate it paints a picture for us. Okay, let's see. As the confidence level increases, the corresponding margin of error increases. So this kind of will make sense. Here's what we're talking about. Okay, this guy right here. As the confidence level increases, my margin of error is going to increase. If I want to, there is a huge difference between saying, hey, I am 75% sure versus 90% sure. So 75% sure, that gives me a pretty loose window. So you got to remember this. Alpha, how do we draw alpha? If I'm 75% sure, then alpha is the percent I'm not sure, maybe. It's that 100% minus 75. So alpha is 25%. So if we're looking at a graph, alright. So here's somewhere we believe the mean is 25%. That means I'm going to have 12.5% here and 12.5%. So you split alpha into two tails, half on the left, half on the right, and it gives you kind of the windows here. This is where you believe the mean to lie. Now if you're 90% sure, that means your alpha is 10%. That means this. That means your tails, instead of having 12.5% on each tail, you only have 5%. So now look, that, I guess I shaded just the opposite. Your window is going to be, so if I go 5% and 5% here, my window is going to be much larger. This is a longer window. This is a tighter, narrow window because my confidence level's pretty small. So hopefully that kind of makes sense. This is a lot of blah 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 blah. You can work backwards. And a lot of times this is what you're going to do. You're going to work backwards. You're going to establish your own margin of error and work backwards to figure out how many people you actually do have to survey. So let's go over a couple of these problems. Okay, so this is kind of getting repetitive. We've done a lot of these, but they're pretty good, where they just sit and prompt you for piece by piece by piece. So here we go. Use the following information to answer the next 14 exercises. The mean age for all Foothill College students for a recent fall term was 33.2. Population standard deviation has been pretty consistent at 15. Suppose that 25 winter students, so that was fall term, so now we're in winter term, were selected at random. The mean age of this sample was 30.4. We're interested in the true mean age for the winter kids. Okay, so here we go. So X bar, so this is the average of the sample. So we're going 30.4 30.4 there, and my sample was 25, and what had a value of 15? The population standard deviation, so that's sigma. Sigma is 15. Okay, so in words, let's describe the random variable x bar. Okay, that's different than x. So x bar is going to be the average age from that 25 sample of student from 25 sample. Okie dokie, 27. Okay, this is a good question. What is x bar estimating? So this average age is actually estimating mu, which is the population average. So we're just taking a sample average, and we got a sample. How large is our sample? 25. I don't know. It depends on how many kids are at that school. If it was 25 out of 200, that'd be a pretty big sample. But if there are thousands and thousands, that's a pretty small sample. So the larger the sample, the closer you can get to estimating what the population mean is. Okay, is sigma from the population known? And that is 15, so it's a yes. Okay, now we're going to construct a 95% confidence interval for the true mean age. Now that's the population, so we are estimating the population mean. So here we go. This is all, well, I guess we can start it off. Okay, 95% confidence level, that means this. We are going to have, let's see, alpha is 0.05, so that's 5%. The left tail and the right tail are going to be 0.025. So 0.025 here, 0.025 here. Boom, 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 boom. So that is that's not very much at all. So that means I'm going to have a huge kind of range here. Okay, so let's find the lower limit, the upper limit, and the error bound, and that's all calculator. So on your calculator, we are going to go menu 6, and you're going to go 6 again, confidence interval. And this is where we talk about the difference between a z-test and a t-test. A z-test is when you have the sigma, t-test is when you don't. So I'm going to choose a z-test because they did give me the sigma of 15. And how we're going to input our data, we are going to input by stats. We've already got the stats. They have given us the stats. So the sigma is 15. We did a sample of 25 kids, found their age to be 30.4. N was 25. Confidence interval of 95. What did they want? 95%. Okay. Hit OK. Okay, so here is my lower limit, 24.5, upper is 36.3, so let me write that down, 24.5, 36.3, so that means this, 24.5, 36.3, my error bound, my margin of error, 5.88, okay, so my margin of error is 5.88, so here's what that means. Your mean, if I go 5.88 this way, boom, 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 and I can go 5.88 this way. So, my range, I can estimate with 95% confidence that my population average, the true mean of all those kids, is going to fall somewhere between 24.5 and 36 and 3/10. Okay. Alright. Okay, so this is referring to the same stuff. So fill in the graphs of the confidence level. We are at 95%. The tails, 0.025 here, 0.025 here. Where were we? Let's see. The left, this was 24.52, and this is 36.28. And now this middle, I don't think it gives us, does it? Oh, let's look at the calculator. Does it give it to us? Oh, yep, it does. Okay, 30.4. 30.4. Oh, that's what we knew. Okay. So look. 30.4, but if you don't know what it is, you can take your margin of error was 5.88. So you can take, if I go 24.52 and I add 5.88, that is going to be 14.5. There we go. So your margin of error is 5.88. That means 5.88 this way, 5.88 this way. Okay, so I think we just did, I think we've done 35. Explain what the interval means. The interval means this. So this range contains, we're 95% sure that it contains the true population mean of those, the age of those students. Okay, let's look at 36. Using the same mean, so the sample mean, we're talking, I guess they gave us this sample mean, 30.4, and the standard deviation, and the level of confidence. Suppose that n were 69. So we sampled 25 kids. So if you more than double that, if you sample 69 kids, if you increase your sample size, what is going to happen to this margin of error? Is your margin of error going to become larger, or is your margin of error going to become smaller? And intuitively, we hope it's going to become smaller. The more people we talk to, the more accurate it's going to paint a picture. So let's try it real quick. Let's go menu 6. We're going to do a z-test. We're going to run the stats ourselves. Okay, sigma was 15. X bar was 30.4. Now our sample is 69. Dude, I think I know why it's not working. Okay. So let's try it again. Menu 6. Z-test. Stats. Okay, I've got to click the mouse instead of the keyboard. Sigma 15, X bar 30.4, and 69. Click the mouse. Okay. There we go. Okay, your margin of error now is 3.5 instead of 5.8. So just by increasing your sample size, your margin of error goes down. And that is what we want. You want the tighter the window you can get, the more you can feel good about your results. So let's see, where are we? Okay, what about 37? Using the same mean, the same standard deviation, and the same sample size, how would the error bound change if the confidence level were reduced to 90? Okay, if we change it to 90, the confidence level, so here's what's going to happen. Oh, the error bound. How's the error bound going to change? it should get smaller. So we kind of talked about this at the first. Let's do 90% versus 95. Okay, to 90%, I've got 5% here and 5% here, so that's 10%. Boom, boom, boom. So my range is in here. If I go 95%, I've got 0.025 here, 0.025 here. So versus 5 from 5, 2.5, 2.5, this is gonna be bigger. So let's calculate. Let's run the stats on the calculator. So we're gonna change the margin of, or your confidence level, to 90%. Here we go. Let me get out of here. Let's go menu 6. We are gonna do a z-test from stats. Sigma is 15, X bar is 30.4. We're not changing the sample. We're just using 25. Okay, the confidence level, instead of 95, let's go 90. Okay, so your margin of error is 4.93 versus, where was it? Where's the one that was 5.88? There it is, 5.88. So we kept everything the same. 15, 30.4, 25. We did 95 versus 90. And if you're going to loosen your confidence level, that's going to tighten everything else. So this one, with a 90% confidence, I've got a tighter window here. 95%, it's just a little bit wider. Okay, 98. A sample of 16 small bags of the same brand of candies was selected. Assume that the population distribution of a bag weights is normal. The weight of each bag was then recorded. The mean weight was 2 ounces with a standard deviation of 0.12 ounces. Population standard deviation is known to be 1/10 of an ounce. Okay, so they took a sample of 16 bags and they weighed them. They found the sample mean, that is X bar, so that's 2 ounces. And the sample standard deviation, that is S sub X, that's 0.12. Sigma, they gave us, that's the population standard deviation, that's 0.1. And we're off. So B, okay, B and C are good because they just keep asking you over and over again, what's the difference between random variable X? Okay, the random variable X is going to be the weight of a bag, any bag from the population. Okay, now X bar, that is the average weight from the sample of 16. Okay, D, what distribution? Now, because it's just a sample, we're going to use the central limit theorem, so we're going to go here. X bar is going to be a normal distribution. Now the population mean, we're going to use the same as the sample mean, so we are going to use 2. And for the standard deviation, you use the standard deviation of the population, 0.1, and divide that by the square root of 16. Okay, now to do a confidence interval, we're not going to do much with that. So now E, construct a 90% confidence interval for the population mean weight of the candies. That's all calculator. So we are going to go menu 6, 6. And we're gonna do a z-test with stats. Okay, sigma. Sigma is 1/10 x bar is 2. 16 was our sample confidence level. Okay, this time they want a 90%, so we're gonna go 0.9. Hit OK. And there we go. And we're not gonna sketch graphs, so state the confidence interval. Confidence intervals here between 1.95 and 2.04. Margin of error is 0.0411. So I'm not gonna write it down. We're gonna save time that we just answered. Boom. We're not gonna sketch that, and we answered that. So now we're on to F. So F, construct a 98% confidence interval for the same stuff. It is pretty simple. You're just going to go menu 66, enter. We're going to do it from stats. Sigma is a 10th. X bar is 2 ounces and a 16. We're going to change that to a 98. So we are going to be more sure. We're 98% sure that the mean lies here, between here and here, instead of 95. So if we're going to be 98% sure, that's going to open up our window. So hit OK. Now our window, so look, our window from before was 1.95 to 2.04. Our window now is 1.94 to 2.06. So it's wider. It's a wider window. And our margin of error is 0.06, and this margin of error was 0.04. So we've got a larger margin of error, and that is because our window is wider. Because we want to report to the boss with 98% accuracy instead of 95% accuracy. So if I'm going to be more accurate, means my window is going to be wider. My lower limit and my upper limit, that range is going to be a little bit bigger. And within that range is going to lie the true average weight of bag of candies on the population. Okay, so we just did G and F. G and H. Okay, now this is a good problem. This one, the average height of young adult males has a normal distribution, standard deviation at 2.5 inches. You want to estimate the mean height of students at your college or university to within 1 inch with 93% confidence. How many males must you measure? So how many males do we have to sample? And that is this. We have got to use this. So let me copy that down. Let's erase this. Okay, now here we go. And this is kind of fun. So here we go. We need N. How many kids are we gonna sample? Okay, we need a z-score. We do not have. We need sigma. We do have. Standard deviation of 2.5, so sigma is 2.5, and we need a margin of error. So your EBM and what's my margin of error? You want to estimate the mean within 1 inch. So your margin of error is going to be 1. That means boom, boom, boom. You're going a half an inch this way, and you are going a half an inch this way. So you want to be within 1 inch. Okay, 93% confidence. wonder if we're gonna, I don't even know if we, oh, I think we are gonna need that. Okay, now check it out. This, we're gonna need that to find your z-score. Okay, your z-score, so you gotta remember the charts. We always start with a mean of 0 and go 1, 2, 3 z-scores and so on and so forth. -1, -2, -3. Okay, the z-score, if I want a 93% confidence interval, that means this. Boom, 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 boom. Okay, 7 alpha is going to be 7%, and that divided by 2 is going to be 0.035% on the left and 0.035% on the right. Okay, now I don't know where that falls as far as the z-scores. So we're going to use the calculator and tell us that. So I'm interested at this point right here, 0.035, because I know the left tail has 3.5%, the right tail has 3.5%. So here we go. We're gonna go menu. I guess I better escape. Okay, now let's go menu 6, and here's what we're gonna do. We're gonna do a distribution to find z-scores. We're gonna inverse the normal. The area is 0.035, but your mean, we're going to leave it at 0 and standard deviation at 1, and that will give us a z-score. So my z-score is a negative 1.8. Okay, now this is cool. Watch this. So z-score is negative 1.8, negative 1.8. So that means this. I'm going to go negative 1.8. Boom, that's like right here. And I'm going to go positive 1.8. So that is right here. So here we go. So with the 93% confidence level, I am within 1.8 z-scores up, 1.8 z-scores down of the mean. Okay, so that's different than your margin of error. So here we go, let's calculate it. So you're going to go, you plug this in, negative 1.8 squared times sigma 2.5 squared divided by your margin of error, which is just 1 squared, boom, 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 and that will tell you how many kids you need to interview. And it's like 20.52. So you are going to talk to 21 kids. Alright. Okay, point 2. Now we're going to introduce the student t distribution. So the student t distribution, in many cases the researcher does not know the population standard deviation. So this is more often than not. We don't know the population standard deviation. So we're going to use a t-test. So in these cases, it is common to use the sample standard deviation, which is S sub x, as an estimate for sigma. But the normal distribution creates accurate confidence intervals when sigma is known, but it's not that accurate when we use, if you just substitute the standard deviation of the sample for sigma, it's not that accurate. So this Irish guy came up with using a t-test, and I think once again, I mean, our calculator is going to do all of this. There's really, I don't think we're going to need to know this. No, in the t-test, there's the t-score follows a t distribution, so this is a t distribution. Okay, we do need to know that. T distribution with n minus 1 degrees of freedom. So remember that. N is how many is in your sample. And blah, 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 blah. So here is our t. Uh-oh. Do we write down the t distribution? Maybe we don't need it. Okay, let's plug along and see what we got here. Okay, 107, a pharmaceutical company makes tranquilizers. It's assumed that distribution for the length of time they last is approximately normal. Researchers in a hospital used the drug on a random sample of 9 patients. The effective period of the tranquilizer for each patient in hours was as follows. So, if we're talking about X bar, well, I guess we're going to have to calculate it. We're going to have the calculator do that and that. We can do N. N is 9, and N minus 1 is 8. Okay. Now, here we go. Let's do B and C real quick. So the big difference between X and X bar. X, okay, X is, what did we were measuring? Length of time. That the tranquilizers last in the population. So for one person. From the population. Now X bar, this is the average time they last for a person from the sample of 9. So that's that's a way small sample. Okay. What should we do? Let's see if we can do D. What distribution should you use? We're going to use a t-test, the student's t-test. Construct a 95% confidence interval. Okay, we're going to have to calculate now. So here we go. Let's go menu, 6, confidence interval. Okay, we're not going to do a Z interval, we're going to do a T interval because we have no idea what the standard deviation is from the population. Oh, you know what? We've got to do it from data. So I got to cancel this. Okay, we're going to have to go home. We're going to have to insert a list. And we're going to have to enter that data in ourselves. So name your list, whatever you want. Boom, boom, boom. Okay, now we're going to punch in these 9 values, and 9's not bad. So we got 2.7, 2.8, 3, 2.3, 2.3. Okay, you got to double check it. Okay, so I'm happy with that. So now I'm going to go yellow, left, go back to my calculator. Now I'm ready. So let's go menu, 6, confidence interval. We're going to do a t-test, and we're going to do it from data. Okay, they want to know, so this one's easier. What list do you want to look at? That's where I want to look. What percent are we making here? 95%, so hit OK, and there we go. So our lower bound is going to be 2.2666, 2.7555 is the upper bound. Your X bar is 2.5, and this, so S sub X, this is your sample standard deviation. So this is 0.317. So now we can answer I. So X bar, that was 2.51. Standard deviation was 0.318. A 95% confidence interval, we got it. That was from 2.27 to 2.76. I'm not going to sketch the graph. The error bound What was the error bound? The error bound right here. This is your measure of error. So margin of error, okay, 0.244. 0.244. So what does it mean to be 95% confident? We're 95% confident that the average time a tranquilizer is going to last in the population falls within this window. Anywhere from 2¼ hours to 2¾ hours. Okay, 108. Suppose that 14 kids who were learning to ride two-wheel bikes were surveyed to determine how long they had to use training wheels. It's revealed that they used them an average of 6 months with a sample standard deviation of 3 months. Okay, so X bar is 6, the sample standard, that's 3 months, and 14, so your degrees of freedom, n minus 1, is 13. Okay, again, what is the difference between random variable x and x bar? So this is number of months kid used training wheels. And x bar is the average number of months kid from the sample of 14 used training wheels. So we're starting to get pretty good at recognizing when to use central limit theorem and when to use just a normal distribution. Okay, what distribution should you use? Now, let's see, what do we got here? Are you going to use a z test or a t-test? And we are going to use, because we don't have sigma. If you got sigma, use the z-test. We are going to use the t-test. Okay, now they want us to construct a 99% confidence interval, so that's pretty easy. It's all calculator, menu, 6, 6. But we have got to do a t-test. We're going to enter our own stats, so they want the x bar. X bar was 6, sample standard deviation, that was 3, and it's 14, and they wanted a 99% confidence level. So the window's going to be a little bit wider. So anywhere from 2... Dude. Did I do that again? Holy crap. Oh. Okay. 6 z-test, data stats. 6, 3, 14, and we want a 99, and I'm going to hit OK. Alrighty. See, what did I do, man? So this, it's kind of messing me up. No, it tells me the x bar is 3 months, but the holy crap, x bar is 6 months and the standard deviation is 6. I messed those up. So negative 1.1 months to use training wheels. That's pretty sweet. That means they can already ride their bike before they even hopped on a bike. Okay, so that was an alarm. I think figured out why. Okay, now we're doing the t-test, and we're gonna go stats. X bar is 6 months, 3 months, 14.99. Okay, let's see what this gives us. Okay, that's better. So 99% sure that it's going to take a kid 3.58 months up to 8.4 months. So that's a pretty big window. to learn how to ride a bike using training wheels. Paching, paching. Okay, let's move on. Okay, last one from chapter 8. A population proportion. Okay, there's a lot of stuff here, but proportion. This is going to be qualitative rather than quantitative. So this is kind of discrete versus continuous. Okay, so proportions. These are kind of, they follow binomial feeling distributions. So here we go. There is a lot of stuff here. All this is calculator. Our calculator is going to do all of this. And I don't think they're going to do anything on the final with a +4. But a +4 is just an attempt to get more accurate. So you add 4 people to the sample. 2 of them are successes. 2 of them are failures. I'd be surprised if this shows up. We want this. Put this in your note card. This is a distribution for a proportion. It follows a normal distribution. P is the percent of success, and then your standard deviation is going to be the square root of P times Q divided by N. And then maybe to find N, kind of like we did, if you know your margin of error, how many kids am I going to have to talk to? This is how you find N. But I'd be surprised if they put this on there. So let's do a couple problems. Alright, number 120. An article regarding interracial dating and marriage recently appeared in the Washington Post. Of the 1,709 randomly selected adults, 315 identified as Latino, 323 black, 254 Asian, 779 white. In the survey, 86% of blacks said that they would welcome a white person into their family. And I'm going to stop there because that's all we're going to do. So A, we're interested in finding the 95% confidence interval for the percent of all black adults who would welcome a white person to the family. So here we go. Dun, dun, dun. Okay. A. Okay, how many blacks did we talk to? Right there. So N is 323. And 86%, so I need to know what is 86% of 323. So you just times them. Times them together. Did I write it down? Okay, that is 277.78. So I'm going to round that up, and I'm going to say 278 blacks said they would marry somebody or welcome a white person in their family. Okay, so here's what I want. We need a 95% confidence interval, but this this is a proportion, so this is totally different. So on your calculator, you are going to go menu 6 confidence interval. Okay, now it is not a z-test, so we don't have a standard deviation. It's not a t-test. It is going to be, if you keep going down, it's going to be a 1 proportion z-test. So here we go. So how many successes were had? And that's what I rounded up to 278. I'm going to say 278, and I don't think it'll, let's try it, 277.78. It's not, I don't think it's going to let you. And 323, 95% confidence, it'll go, no. Yeah, so it's binomial. So it's got to have a discrete number, not a continuous number. So here we go. Menu 6, proportion. Okay, so we're going to round up to 278. N is going to be 323, 95%. Okay, so your lower limit is right here, 0.8229, 0.898, the p hat, your proportion, so it was 86% said they would, so we're 95% sure that anywhere from 82% to 90% would be okay with that. So your margin of error is 0.0377, and that looks pretty good. So now let's go back here to the question. Okay, B, what distribution are you going to use? We're going to use a t-test. Excuse me. So we're going to use, oh no, yeah. We're doing proportions. We're not doing standard deviations. Okay, we're going to use a proportion. We're going to use this guy right here. Now this guy, so B, so this proportion has a normal distribution. The average is going to be, we'll call that 86%. Average is your P. Your standard deviation is going to be the square root, all of this under the square root, so 0.86 times 0.14, so P times Q divided by 323. So that's what the distribution looks like. C, we already did all that. Okay, 130. On May 23rd, a Gallup poll reported that of the 1,005 people surveyed, 76% of U.S. workers believe that they will continue working past their retirement age. The confidence level was reported at 95% with a 3% margin of error. Okay, so determine the estimated proportion. That's going to be 76%, so 0.76. Determine the sample size, that's 1,005. Identify the confidence level, that's 95%. And alpha is 5%, 0.05. Okay, calculate the airbound. So let's do this. Let's go. Whoops. Let's try it on the calculator. Here we go. So we're gonna go menu 6. Okay, you gotta come down here and do prop test. Okay, number of successes. Oh, so let's see. What was it? 76%. 76% of the 1,005. I'm gonna type in. I've already got it. 764. N is 1,005, and we're gonna go 95% confidence level. Okay. So from the sample, here we go. 0.733 is the lower limit, upper limit. P hat, 76%. And the margin of error is going to be 0.026. Okay. So the error bound was actually 0.026. Compare the error bound to what we found, to what the Gallup poll said it was 3%. So 0.03 versus 0.026. So they just rounded up. They said it was 0.026. 2.6 is close enough to 3, so they rounded up. Create a confidence interval, and we did that. So a reporter is covering the release of this study to the news. How should she explain the confidence interval to her audience? So, I don't know, we just got a sample. We're going to use this sample to estimate what the true proportion of the population is. So we talked to 1,005 people. The true proportion would be all U.S. workers across the entire U.S. So that's millions and millions and millions. Our sample's kind of small compared to the millions and millions and millions, 1,005, but we're just using this sample to estimate what the true proportion would be. So we believe with 95% accuracy that the true proportion of U.S. workers 0.73, 0.79, 0.73, 0.79, 0.79. Anywhere from 73% to 79% of all U.S. workers believe they're going to have to work past retirement. Okay, last one. A national survey of 1,000 adults was conducted. It concluded with 95% confidence that 49 to 55% of Americans believe that big-time college sports program corrupt the process. Okay, this is an awesome problem. So the point estimate, who knows? We haven't really talked much about a point estimate. I mean, we kind of have an error bound for this confidence interval. So 49 to 55. Okay, so anywhere in that window here. So I want this. That's our point estimate. That's what we're talking about. What's the one right in the middle? What's the mean? So 49, 55, add them up, divide by 2. We get 52. So 52%. That means 52, 53, 54, 55. This is plus 3. Boom, boom, boom. This is minus 3. So the point estimate is 52%. B, can we with 95% confidence conclude that more than half of all Americans believe this? Well, more than half would be 50. So if your window was from 50 to 55, it'd be yes. But because we include 49, your answer is no. C, use the point estimate from part A and a sample of 1,000 to calculate a 75% confidence interval. Okay, 75% confidence interval. So we're going to go menu, 6, and we're going to do a prop test. Uh-oh. 75% of 1,000, so that's going to be 750 successes. Of 1,000. Oh wait, no. Use the point estimate. The point estimate was 52. This is 75. This is for my 75. 0.75. Okay, so your point estimate is 520, 52%. Okay, here we go. So your lower limit's going to be 50.2%. Your upper limit's going to be 53.8%. Same point estimate. This is your point estimate, p hat. Wow, my margin of error is 0.018. So the question is, can we, with 75% confidence, conclude that at least half of Americans believe this? And your answer is yes, because my window is 50 to 54%.